Hi, everyone. So I'm going to go over a few of the graphs that we've been learning. So it's going to be from some of the previous lessons that we were doing on Wednesdays that maybe you were not here for. So, um, and once you get your packets, this is on in the first packet, um, but this is data that we kind of made up before because we didn't have as many people. So it would have been nice if you guys were in there, but oh well, that's fine. So how many pairs of shoes do you own? All right, and so we recorded, so there were some of these numbers. So some people, one person had 3, 4, 1, 11, 12, 4, 3, 3, and 12, okay? And we asked ourselves, well, is this categorical data or is this quantitative data, right? Or I guess I should say variable, the categorical variable or a quantitative variable. Now categorical, remember it's in a category, like, right? Is it blue or what's the color, right? If it's a color, then that's categorical because they are in categories, right? And a quantitative, like think of quantity, right? What is the quantity? We think of a number, right? So numbers usually will represent the quantitative data. And so yes, this is going to be quantitative data. All right, and we were supposed to, we looked at Staplet, but that's fine. We're gonna just make a dot plot, a stem plot, and a histogram. So those are the 3 that we're gonna go over. And then we're gonna go over some of the other ones in another lesson, right? And the way you make a dot plot, first make a number line, right? So here you see our number line, it's in the same intervals, right? So we're just going up by ones. Smallest number is 1, going all the way up to 12. You don't need to go any more or lower than that, right? And then we just put a dot for each of these data points. That's it, right? And again, if you notice right here, all the spacing should be the same. So it's the same distance above that line as well as from each other. Okay, so that's always going to be the same. So it should be accurate. So you're like, oh, this one, so it should not be like munched in. So like if you had one like this and it was like super like, I went, let's pretend, right? And if I went like that, to see how that's the same height as the 2, that should not happen, right? So they should not be, because this should represent 3. Ooh, that should represent 3, and it should not be that like pushed in together. Okay, so the one with 3 should be higher than the one with 2, and in equal amounts. Okay, so that's one thing to remember about that. And we're going to also label this. So this was the number of pairs of shoes. Ooh, I don't think we did that for today's lesson, but we can do that later on. All right, and then that's how you make a dot plot. All right, and then the way you make a histogram is here we have the frequency. So this is going to be like how, let me just write down frequency on here. So if we do it sideways, oop, probably not with that kind of a thick. So I'm going to say frequency. If you can write that or read that. So that's frequency. So how often does it happen? So we made these things, these are called bins, right? So is this going to be from 0 to before 2, less than 2, right? So we're not including 2 because 2 is going to be for the next bit, right? So this can be basically 2 and 3, or anything less than 4. And then same thing, so on and so forth. So those bins need to be the same increments, okay? You can't have one bin be like, oh, represent 1 number, and then the next bin is going to be represent 3 numbers, right? So if you look for here 3, where would 3 go? Oh, it would go in here. So from 2, so they would have 1 frequency just like that. So it would just, oh yeah, we got 1. Or this is what I would have done. So I go, okay, from 0 to 0 and 1. How many of those do we have? Oh, we have just this one right here, the 1. That's why it's frequency of 1. And then from 2 to 4, so not including 4, how many do we have? We got 1, 2, 3. So that's why we have 3 there. Okay, so, and then you would do that. So notice we have nothing here. So apparently for the people that we had, nobody had between 6 to 9 pairs of shoes. It didn't happen, right? It was either a lot or a little. And there was no in between apparently, right? And I'm curious to know where you were in that, right? And here again, we're labeling this. And then also now we're gonna do the stem and leaf plot. In this stem and leaf plot, it doesn't look very interesting just because we only went up to 12, right? So again, we put 0 here because technically in the tens place we have a 0. It's like 0, 3, right? So we're just gonna write them, and notice all of these are in order. So what usually happens is, if I were to write this out, I would just write these in. So this would be 3, this is 4, This is 1, and 11, remember, is 1, 1, and 12 is going to be 1, 2. So this is our tens place, and this is our ones place. Okay, and then 4 up here, 3, 3, and then 12, right? And notice right here, it's all not in order, right? But for a stem and leaf plot, where the left-hand side, on the left-hand side of that, that line is the stem, and on the right-hand side are leaves, right? We have one stem, many leaves, right? Or maybe no leaves, depending, right? Notice right here, it's not in order, so we need to put them in order. So not only do you put them in order, but if you notice right here, let me put this in green. So this, you see how the columns are all lined up? They should all line up, okay? So just like the dot plot, we're not mushing them in so that we can see this, if we can see the longer it is, the more data it has in there, okay? So that's one, it's like a bar graph with information or a histogram with information, right? Because in here, we don't know what number this was, but the stem and leaf plot tells us the number, right? So if you want to think about, so in other words, we could be like, okay, this is like a histogram. That's one bar, and this is, let me do yellow. This is the other bar, right? So think, oh, these ones have a lot more in here than it does the other one. Like our bins are like, yeah. Anyways, so that's one way to think about that, okay? And that's how you would do a stem and leaf plot. Make sure you put them in order, okay? That's really important. And if we have like, this way it's really easy to tell what the mode is. Not that we would need the mode, but it's really easy to tell what that is because it's like, oh, in a straight line, there's 3 3s, right? The mode. That's pretty easy. And then remember, we always need the key. You always have to write in a key because if you don't, then that's gonna not, I was like, did I not show my screen? I freaked out for a little bit. I'm like, do I have to start this video again? Oh dear. And so we're always going to write that key. So in this case, it says 1/2 means 12, right? And so this means 1/2 is 12. You can use whatever numbers in here. It doesn't matter what numbers you use, as long as you use 2 numbers. So if I say like 2/5, even though I don't have a 2/5, it doesn't matter, right? But I'm going to say that means 2.5, right? So now these take on a whole different meaning. So now this is going to be 0.1, 0.3, right? So that's why the key is really, really important. Or if I said instead of 0.5, it would be like 25 or 250, right? And then so I would say, oh, I know that this is going to be, this is a little bit harder. So no hundreds, and this be 1, so this would be 10, and this would be 30, and this would be, because literally this is just going to be, because this is going to be 0, 3, 0, which we know is 30, right? We don't normally put the 0 in there because it's irrelevant. And this number right here would be 120, right? So again, it depends on what you have as your key. Obviously, this is not 100. If I had 120 shoes, that would be nice, but I don't. All right, so there we go. I'm just going to delete that because that's not our key anymore. We don't want to confuse people, right? So we're always writing the key. Let me move on. And again, we learned about how to describe distribution, right? And it was the shape. So we're doing this SOCV, so SOCV plus content, right? So the shape, the outliers, the center, and the variable. What is the shape, right? It's either going to be, in this case, we're going to say, oh, it's slightly skewed right? Even though we don't have a middle part, but it's like pulled to the right. So here we have the different types of distribution. So we have it's symmetric or fairly symmetric, we would say, because nothing is exactly symmetric, nothing in real life, right? And then if it's pulled to the left, then that's skewed left. Okay, so this one, I'm going to just write it over here. I'm just going to go. So this one is, what was I doing? What did I say? Oh, symmetric. Oh my goodness, I was thinking normal. I'm like, no, that's something else. Okay, so this is symmetric. If it's pulled to the left, right, that means it's going to be skewed left. I always want to do it the other way around, right? I always want to say if the big bump is on the right, then that's skewed right. I'm like, no, that's not correct. It's the tail. So think of it like pulling. I remember a lot better when I think about pulling. So if it's pulled to the left, that's skewed left, right? And if it's pulled to the right, so if it was symmetric and then we just pulled that like a string, right? Then it's going to look something like this. Then this is called skewed right. Okay, so these are the three basic patterns that you're going to see when you're describing distribution, right? And then remember outliers. There are no apparent outliers is something that we could say, you know, there's nothing that's extremely large or extremely small. And we did learn a little rule for this, right? It was 1.5 IQR, but we won't talk about it just yet. And then remember, center is either going to be the mean or the median. We don't normally use mode. Okay, so this is going to either be mean or median. So I would write that in your notes somewhere, mean or median. So normally when we're talking about symmetric, if it's symmetric, we normally use the mean. Okay, and then we'll learn why we do that later on. And then for anything that's skewed, so it has some really big numbers or small numbers. Skewed left would be really small numbers. Skewed right is really big numbers. We would use the median, because the median doesn't get affected by outliers as much, right? Because remember the mean, like we combine all that data and then divide it by however many we have. So if you have really big numbers or really small numbers, it gets affected, right? Pretty big. Because if we had numbers like 1, 2, 3, and then one of the numbers was 100, right? Now that totally skewed our data. Right now our median, our average is a whole lot bigger than it should be, and is not representative of what actually is happening with a lot of people, right? And then, but the median, it just cuts it right off, right? Just cuts out the end, so the outliers really don't get counted. So that's why the median is better for skewed stuff. So this one, we would use the median, okay? And then, let's see, oh yeah, our variability. At this point, we had only known about the range, so we just talked about the range. Remember, the range is just the biggest number minus the smallest number, and the number, that number 11, that's the range. It's not, oh, from 1 to 12, that's not the range. Okay, that's like in everyday colloquial language. For us in statistics, when we say, what's the range? We want to know, what is that spread? Like, what is the number difference, right? So it's just 11, okay? So the difference between the biggest and smallest number, it's 11, right? So if we knew the range was 99, we're like, oh, it's a really big spread, right? Because it's from what, it doesn't matter what the biggest and smallest number is. We know that the difference between them is going to be 99. Okay. And then I think that was all for this one. Yes. Oh, also, did you know we can do a side-by-side stem and leaf plot, right? Here they call it a stem plot, just to make it shorter, but you can say stem and leaf plot. That was the original wording for that. And if you notice right here, we can have one on the left or one on the right and one on the left, okay? And here was the teachers versus students, because I was wondering, well, does it make a difference with the students? Because my theory was, I was thinking, we'll talk about it later, about theories and all that kind of stuff, is that students would have less shoes than teachers do, because I'm assuming students don't have as much money as teachers do in general, or they're not as old as teachers in general. So we're going to have more shoes if we like shoes. And so notice right here, yeah, I'm like probably the 22, or was it the 35? I like shoes. So again, notice right here, so just make sure you're labeling which side is which. Do the teachers have to be on the right? No. The students could have been on the right, but you just need to label that. Okay, so students here were on the left and teachers were here on the right. And if you notice right here, we have a key, right? And we did label it number of pairs of shoes, and 27. So 2/7 means 27. So we know what these numbers represent. And notice right here that we do line up the columns, right? So there's a little bit squished in right here, but they're both squished in at the same amount. But it should be the same amount of spaces. So I apologize for that. And so that's what that's going to look like. And if you notice right here, definitely the teachers have a bigger range, right? So now we're going to compare the distribution, right? And whenever we're comparing, we're going to be using comparative language, right? And what does that comparative language look like? We'll talk about that. So the number of pairs of shoes for both the teacher and the student are slightly skewed right. So if you notice like this, it's slightly pulled on the bottom, right? So it's slightly skewed right. And we have, so we need like these ly words like slightly, and then we described as skewed right, right? And notice we're comparing, so we're going to use comparing with green. So both both the teacher and the students, right? If there was no both, then we're just stating it. We're not comparing. And that's apparently a big deal because on the AP test, they look for that. They look for these comparison words. Okay, and then right here, outliers. Neither of them have any apparent outliers. We don't have a system for that at this point, right? So we couldn't say anything about that. So here we say neither have any apparent outliers. And the center, right? So the median, the way we check for the median is, remember, we just find the middle number. And if you look, we're going to count from the lowest. So the lowest number is 6 and the highest number is 35. So it's 1, 2, 3, 4, 5, 6, 7. This is the 7th number. And I'm going to count backwards. 1, 2, 1, 2, 3, 4, 5, 6, 7. This is also the 7th number from the back, right? Which means the median lies right here in the middle, right? And the way we calculate that out is we're going to go not 2 plus 3, because this is not actually 2 and that's not actually 3, right? Remember, this is 12 and 13. So in between 12 and 13 is 12.5, right? So, or you could just say, let me just put it right over here. So 12 plus 13, divide that by 2, which is going to give you a 12.5. Or if you want to really like get technical about it, right? So that's what that's going to do. Do you need to show that work on the test? No, but it's good to know. And also here on the left-hand side, we want to know what the median is. And so we're going to go 1, 2, 3, 4. This is the 4th one. I think it is. I don't remember. So this biggest one is going to be 1, 2, 3, 4. And then this is the 5th one. So this right here is going to be our median. So the 4, that's what we have, median of 4. So which one is higher? Well, I would have known that anyways, but the 12.5 is obviously higher. Teachers have a higher median. So that's what we say, the median for the teachers is higher than the median of the students, right? Do we need to state what the median is? No, we don't need to state it. We just need to state that it's higher or lower or whatever it is, right? So here we have our, go back to my highlighter. See our higher than, right? And yep, that's our comparative word, right? And then variability, right now, so far at this point, we only knew about the range. So we talked about that. So the range of the teacher's number of pairs of shoes is higher than the range of the students. If you wrote it the other way, right? The range of the students' number of pairs of shoes is lower than the range of the teacher's number of pairs of shoes. That was fine. It doesn't matter which way you go. You don't always have to do the higher than. I was just going with a pattern, so that's fine. Okie dokies. And so a few things, right? Anything in this important ideas section, I would always write those out or like put them in your notes section or something like that. Okay. So again, whenever you're describing distribution, you got to make sure you use the context. Okay. You can't just say, oh, the medians are higher or the median of one is higher than the other. You cannot say that. You have to say what the context, even once. Okay. Even if it's once, like at the top, that's fine. When you're describing shape, that's fine. Okay, once you describe it once, you're good to go. All right, and then use words like the ly words like roughly, approximately, what was the other, slightly, fairly, like fairly symmetric, like things like that. Okay. So, and also when comparing, okay, whenever it says to compare two distributions, right? Add comparative word language like more than, less than, higher than, less, that is less than, lower than, things like that. Or if they both have the same thing, then you say both, right? Or neither. Any of those are fine, right? And outliers, we were going to talk about that. Remember, this was now, we now know this is 1.5. Oop, still in highlighter mode. This is actually 1.5 times the IQR. Okay, and that's how you can figure out whether we have outliers or not. And so remember, this is skewed left. We have skewed right. I try to draw a little picture of it. And symmetric. Okay, so that's when we're describing the shape. We have outliers. Center, it means median or mean, right? And I showed you when you use which one, right? And variability means how spread out is the data? Like, what is that variability, right? And right now we're just going to use the range, but there's a couple different ways to describe that. I would recommend that you try this out, see if you know how to do a thing once you get your packets, right? Practice. All right, and then the other one is that I wanted to go over, right? This one we talked about this is where do I stand? And we're going to come back to this lesson and we're going to refine it just a little bit in a different piece of paper, don't worry. This is where we learn how to do the box plot. Okay, so if you notice right here, we had all these, we found all the different heights of different people in our household because we didn't have enough data. And so here we plotted them all out. And remember, we want to find the median, right? So the way we found the median is, remember, you put them all in order. And thankfully on this dot plot, it was all in order already, right? Because it's in order. And we found the median. So you literally do one of these, you know, you count one, you take one from each side and you count it off. And we found our median to be between this 64 and 66, which would mean that our median is 65. Okay, it's right halfway in between that, right? And if you did not know that, you're like, I don't remember. Remember, add them up, divided by 2, and that's how you get 65. That's what we wrote here. All right, and then what is our Q1 and our Q3? Remember, it's quartile 1 and quartile 3, right? Which means that literally on, so this is the median, right? So none of these numbers are included in that median. So anything to the left of that median, that's what you're going to do the counting thing again, right? And so we're going to take the median of the left, that's Q1. You take the median of the right, and that would be Q3, okay? And so we found that to be the right in between 62 and 62, which would mean that the median is 62, right? So that's why we got Q1 is 62. And over here, when we went halfway in between, that's going to be 68.5. All right. Notice if, let's say if, ooh, what did I just do? I can do that. So let's say I need that. If this was our answer, but what if we didn't have the 76, right? If the 76 was not there, right? I'm just going to use this in black. So pretend the 76 was not there, right? Then when we when we count in, right? That means this right here is going to be our median. So if we use one of the numbers as our median, we're not counting that for the Q1 and Q3, okay? So we would go from this 64 and we counted 1, 2, 3. That would be 1, 2, 3. So this would be our median, our Q1, okay? And then on the right-hand side, right, we're not including that 64. Be 1, 2, 3, 4, 5. So this one would be our Q3, okay? See how that goes? So if we have an odd number, we would not count whatever the median is as part of the Q1 or the Q3 calculations. Hopefully that was clear. Sometimes that gets confusing, so I'm going to erase all that now. Okay, so now we're going back to our merry way. So now that we have all of our values, right? This is like the statistics summary. I can't say that. So again, we got our minimum right here, so that's going to be 60. We got our max at 76. We can just look at it right here on the dot plot, right? And then we figured out Q1. So I like to draw a line here, draw a line here. And then our Q1 is 62, so I'll literally draw a line here. And then 68.5, so go like, it's gonna be halfway between 68 and 69, right? So 69.8.5. And our median we know is 65. Already calculated that out. So what I like to do is, now that I have these 5 lines that are the same distance above that number line, is the middle 3, you're just gonna connect them. Connect the bottom and connect the top. And that's going to be your box. Now we're going to do the whisker part. That's why it's called the box and whisker originally. And then from the box, the right-hand side of the box, we're just going to connect it to that line. That should be halfway up. Some people put dots here. I just like to put lines. And then you do the same thing with the left-hand side. And that would be your box and whisker plot, AKA box plot. Okay. And so we also learned on this one that we have an IQR. So this is the interquartile range, right? Which we refer to as IQR, all right? And we define that as being, remember, range is still the same kind of range where we subtract it, right? Like how I talked 5 minutes ago, right? And so that's Q3 minus Q1, right? So it's gonna be 68.5 minus 62, which is 6.5. So the length of this right here is 6.5. IQR. All right, and outliers. So remember we said outliers. So this is another thing that you would want to highlight or write in your paper or something like that, right? And way too small and way too big. What in the world does that mean? So we're going to take the 1.5 of the IQR. So we figured out what the IQR was, which was 6.5, right? We're going to multiply that by 1.5 because that's kind of a man-made thing, right? They just said, oh, we're going to do 1.5, and anything beyond that is going to be an outlier. Later on, we'll talk about a different way to figure out outliers, but we don't have that yet. Okay, so, and remember from the Q1, so we're going to go from the Q1, so from the quartile one, we're going to go 1.5 out from here. So that's why since we're going to the left, we're subtracting. All right, so that's what we had to subtract, which was, oh, Jacob, we said Jacob was an outlier only because Jacob was the 76 over there. We're trying to figure out if that was an outlier, right? And so the way we would do, oh, sorry. So we're doing the way too small. So if we're doing the way too small, that's going to be, we don't know that number yet. We don't know what that number is. But way too small is going to be Q1, which is going to be 62. Minus this guy right here, 1.5 times 6.5. We don't know what that is. Let me figure that out. Order of operations says multiply first. Like, that's still a thing? I'm like, yep, that's still a thing. That's 9.75, and then subtract it from 62. If I can do it. And that's going to be 52 and a quarter, right? So this is going to be 52 and a quarter. So anything less than that would be an outlier. Do we have anything less? No, we don't have any super, does 52 inches is like really small, because 60 inches is, what is it? 60 inches is 5 feet, right? So you'd have to be about 8 inches less than that. So like you'd have to be like 4'4". So yeah, nobody was like that in our class or their family members or anything like that. So no outliers on that side, but we did find an outlier with Jacob, because Jacob was above, wait, our IQR, oh wait, do we have that? Jacob is not an outlier. Never mind, I'm sorry. I was like, I didn't read that right. So yeah, so an outlier would have been above 78.25, and Jacob was 76, so therefore, but if you are above 78.25 inches, then you would have been an outlier in this data set. Maybe not in all data sets, but just in this one. Okay. All right. So again, we talked about the what we would do to describe, right? Describe quantitative data with numbers. And remember, S means shape, outliers. O is outliers. C is center, right? And then V is the variability, right? Shape, remember, is like the symmetric, skewed right, skewed left, those kind of things. And then the outliers, or it could be uniform, I guess, if there's like literally, it's like a box, right? It's just uniform distribution, right? And so this is another thing that I would look at, read it, see if you can write something that's similar to it. I told you there's a lot of writing in here. That's why I ended up like just typing it, because I'm like, I can't write. That's like, to write that nice and that much, can't. So I'll just type it. All right. And for you, I don't know if that will be an option for you guys to type it out like there was this time around. So I would get used to work on those finger muscles. All right. And so that was a box plot. And so histogram. Okay, so this was today, right? And so we were talking about Mark McGwire and Barry Bonds, and those are famous baseball players from way back in the day, a much long time ago, right? This is Barry Bonds and this is Mark McGwire, right? I know that because they were from my generation when I was a kid. All right, so here, so it says Barry Bonds broke Mark McGwire's record when he hit 73 home runs in the 2001 season, which is way back in the day, right? 19 years ago. What? How does this accomplishment fit with the rest of Barry Bonds' career? So here, Bonds' home run counts for the years 1986 to 2007, right? So if you look right here, this is what he did. And we were just debating, you can do a dot plot, box plot, histogram, stem. If you did not do this because you were signing up for AP class or whatever, I would just do it now. Just pause, do it now. Okay, I'm assuming that you finished now. And then, so you could have picked any one of those, and oops, I didn't mean those little dots. Okay, so what we're gonna do, I'm gonna make that black. So again, we had done a not a stem, a box plot over here. Box plot, what in the world is this? A histogram. Oh my goodness. This is late in the day, I think. So a histogram we're going to do, I noticed these are called bins again, and they're going from 0 to 20, right? 20 to 40. Remember, this box does not include 40, goes up to 39 or 39.9. But in these ones, obviously, they're all integers, so we can't include 39.9 because there'll never be a 39.9, right? 0.9 of a home run. What does that mean? Right? You're almost there. All right, so that would be our histogram. Let me just go like this. Maybe that'll be easier. There we go. That's all in there. And then, so histogram, remember, they're all stuck together. Bar graphs are the ones that are not stuck together. They're used for categorical data. So think back to like elementary school, like in second grade or first grade, where you like, if you like chocolate ice cream, then, and then you figure out how many people like chocolate ice cream or strawberry ice cream or whatever it is, right? And you would make these keep on saying box plots. You would make the bar graphs, right? So we're not doing those anymore. Okay, so, and these are, again, are going to tell you the frequency, and this is going to be, and we're going to title this, right? So if you did not title yours, make sure you title yours, and this is going to be the number of home runs. Per season, because they were doing, if it was number of home runs per game, the 73 home runs per game, that would have been an exciting game to watch, but no, per season. Okay, so that's how we would title this guy. And we did have our summary statistics down here. This was all from Snaplet. If you want to try that out, check it out. But later on, I'll show you how to do this on your calculator once everybody has a calculator. But we can't do that right now, so we'll just do it by hand. And it's good to do it by hand, because you're going to have to do that anyways later on. Okay, describe the distribution. Remember again. So we have SOC. I said S, but it should have been V, variability. Duh. I'm a ding dong. So yeah, oh, I just erased everything. CV. So this is going to be our variability, which is the same thing as spread, but I want to try to keep that consistent. So I apologize. Variability. My bad. Ability, which is like the range, the IQR, the SD. Standard deviation. All right. And C is going to be our center. Oh, my dear. I'm sorry. So here we go. S, our shape. The distribution of home runs for Barry Bonds is fairly symmetric, right? Because it's fairly symmetric, right? It's not really skewed that much. Maybe, we'll just say it's fairly symmetric, right? With a median, right, of 33.5. If you used mean, that is perfectly fine. Because that describes the center right here. I tried to color code them. And a standard deviation of 15.4. So that's going to take care of our variability. Let me go back to the blue. And so I could highlight that. So these are corresponding. I'd like to use colors to correspond that. So if you have highlighters, and you got highlighters from school, that would be great because they have great highlighters. Yeah, use them to kind of show like so you can see for yourself where these things are located, okay? And then there are no outliers. Yep, when we check that here by using the IQR rule, right? So 1.5 times the IQR. Remember the IQR is the the Q3 minus Q, where's Q1? Right here, right? And I color coordinated them. It's the same thing every time. And the way we compare them, take the biggest, so the 45, right? And no, this is for the other one. So we're taking the 45 and adding it to adding 30 to it, right? Because that was 1.5 times the IQR. And then we got 75. Do we have anything higher than 75? We got 73, but not 75, right? And then same thing with we go to Q1, the 25 minus 30, which would be -5. We definitely have no negatives, right? So we have no outliers. So we will say there are no outliers, okay? And that's that. And then for the second one, so here, for number 5, we have the distribution of the number of home runs per season for Mark McGwire. And so we're going to compare this to the distribution of Barry Bonds. So compare these two guys. And so if you look at both of them, we're like, here, let me see if we can zoom out this a little bit. I'm going to move this. Oops. Move this up just a bit. Just go like right here. Okay, and if you notice right here, so this one is where I did the actual comparison. Okay, we're going to do a little bit of highlighting here. We'll use the same kind of highlighting numbers. Let me read this for, well, yeah. The distribution of home runs for both Barry Bonds and Mark McGwire is fairly symmetric. The mean is slightly higher than for Mark McGwire, as well as his standard deviation, right? So here, where do you see the shape? Right, the shape is fairly symmetric, right? And then where do you see the yellow, which is the outlier part? Outliers, yeah, there are no outliers, right? And then where do we see the center? That is a different color. Let me be, is that this color? Is that this color? I don't remember. Pretend that that's the color. Oh, I think it's blue. Darn it, a pale blue. All right, so that's going to be our center. Do we have the center? Are you looking for mean or median, right? And you're like, the mean, right? Got that. All right, and also we need the variability, which is the range. And we're like, oh, his standard deviation. And so also with the other thing that I would like to check is the comparative language, right? So I'm going to put that in pink, right? Did we compare a thing, right? And we look at, yeah, we have both, right? And we have slightly higher, right? And the reason why I used mean instead of median, right, was because the median for both, oh, right here. So the median for, hello. So the median for both is 33.5. So I was like, I could have said that they were the same, but I was like, let's be a little different, right? So here we use this, and plus it was fairly symmetric, so I should use mean anyways, right? So that's why I said, oh, where the mean is slightly higher for Mark McGwire, right? And as well as his, so as well as, right, is, and then for either distribution. So we do have that comparative language there. So if you wrote yours and you didn't have like comparative language and you're just saying, oh, this one, if it looks exactly like what we wrote up here, then you would, and you did that for both of them, that would be incorrect. You would like not get a lot of points for that because you did not actually compare. So it's really imperative that you follow directions because they're really looking for that. They mean a thing, right? And this was what we did in class. We just were trying to, write one for Mark McGwire, right? And without comparing because we had just learned a thing. Well, for most people. Okay. But this is the one that I'm looking for this when we're comparing two different answers or two different distributions. All right. And for your homework, just make sure that you do the getting to know you survey. All right. Hopefully this was helpful for you. I will talk to you guys later.